Okay. Hi, everyone. So my name's Lewis. I'm CTO of Dataform. We're a pretty early stage startup based here in London, building data tools for data teams to manage SQL-based transformations in cloud data warehouses like BigQuery, Snowflake, Redshift. Previously, I was an engineering manager at Google. I spent most of my time there, like 6.5 years, building data pipelines. We built those pipelines with systems a bit like Apache Spark or Apache Beam, mostly Java-based stuff. We put a lot of time into it. We processed a lot of data. Interestingly, there are no data engineering roles at Google, or there weren't when I left. And I think this is because pretty much everybody who works at Google is working with massive data in some capacity. So these days, we don't use Java for most of our core data processing at our current company, and we're selling products to help you avoid doing the same too. We think there's a new approach. I'm sure many of you heard of it. It's an ELT approach, and it's enabled by modern cloud data warehouses. Oops. So I'm going to go through two things. Firstly, what is ELT? Comparing it to ETL and looking a bit at modern cloud data warehouses and some of the technological changes that really enable this model to work. Secondly, we're going to discuss how we achieve operational scale when most of our data transformation layer is now happening in SQL in our cloud data warehouse. So we'll look at some best practices. We'll also look at some of the disadvantages of using a language like SQL for your core data transformations, and then how we can address that with the right tooling and frameworks. Okay, ELT. Just a quick kind of primer on why we're doing this and what we're trying to achieve as a company. We want to provide a scalable solution for managing data transformation processes that works for data engineers, data analysts, and data scientists, everybody who's part of that core data team. One of those things is we want to avoid having to force people to write code. We know that data analysts, for example, maybe are less comfortable writing Python to do their core data transformations. We think SQL is a great language for this, and I'll talk through some of the pros of that in a minute. Okay, so ETL and ELT. I'm pretty sure everyone's heard of ETL before: extract, transform, and load. ELT is just flipping two of these steps. Both are very similar. It's a subtle difference. We kind of advocate for an architecture where all of your data is replicated into your cloud data warehouse. With a ETL model, you may typically attempt to transform that data on its way in so that you only really push to the warehouse the kind of clean, ready-to-query data sets, and you use a tool to manage that process. In an ELT approach, we're changing it slightly. Rather than transforming that data on its way into the warehouse, we're just dumping raw data into the warehouse directly, and then transforming it once it's in there. This requires slightly different tooling and a slightly different approach, but it has a few benefits. So first off, your raw data is now in your data warehouse if you need it. This can be extremely beneficial. If you miss something in your transformation step, you can go back. You can still look at the raw data if you want to. The extraction and loading process is now dramatically simplified. It's just a copy-paste or a streaming inserts. There's no business logic happening at this step. The infrastructure is a lot simpler, and if you've worked with these systems before, you will know that they can be a nightmare to maintain. At this point, we can now write our transformation layer using SQL, which I think can be a lot simpler than having to do it with kind of code or writing Python. And you also have this kind of overall benefit of all your code being in a single place. So to visualize this architecture, got this diagram together with a cloud data warehouse, and I've kind of listed BigQuery, Redshift, Snowflake, just because those are the ones that most of our customers are using, and the ones that kind of are maybe designed for scale more than other offerings out there. We have an extract and load process, pulling data from external third-party sources. This may be our CRM, our production database, our event logging, web logging systems. All of that's getting dumped in its raw form, in a somewhat messy form, into our cloud data warehouse, in like a staging area, we could call it. At this point, we want to transform the data, and this is the T in the ELT, and we want to turn that into prepared data sets that are then ready to be used for our BI processes, machine learning projects, whoever the consumers of the data are, that data is there, it's up to date, and it's in a fairly good format, ready to be used. So you might be looking at that diagram and wondering, like, that's never going to scale. A lot's changed in data warehousing over the last few years. And we're going to have a quick look at some of the core innovations behind modern data warehouses, which really makes this process scale. Modern warehouses aren't like your traditional SQL database. There are no foreign keys, indexes. They're designed for massive load, and they have to remove some of these to achieve that. And products like BigQuery are claiming that they can handle like exabyte scale these days, which is just crazy. Okay, so there are many things that make warehouses great, but there's two that I wanted to pull out, which I think are particularly interesting and worth talking through. And one of the first things, and there was a paper on this, I think probably like 10 years ago now, around columnar storage, and this is kind of at the core of a lot of technologies, even things like Parquet or Avro files. All of the modern data warehouses are taking advantage of columnar storage formats. So in these two examples, on the left is a kind of traditional row-based format for storing data. There are some arrows, and those arrows represent the order in which the data is laid out on a disk, like on an actual hard disk. If we make a query against one of these tables, such as sum C2, we need to follow the arrows, and we need to go through each row, skipping a lot of the data, but those skips still cost us something. We still have to go through the disk in a linear order, because that's how disk reads work. We end up reading a lot more data than we actually wanted to. And when these tables are extremely fat, which is increasingly the case with the kind of data we're working with nowadays, this is a lot of extra load. In the column-based storage format, we change the direction in which this data is stored on disk. Columns are all stored together, and we keep track of an index so that we can actually join these things up. And in this case, when we want to read C2's data, we can actually just read it in one single block and just ignore all of C1, all of C3's data entirely. This makes these queries extremely efficient, and it's particularly valuable when working with extremely wide tables, which we often are. Okay, so the second kind of key innovation, which not all warehouses do as well as each other, but this is what has kind of, I think, really enabled data warehouses to scale in the last few years, is separation of storage and compute. A data warehouse is the place where you're storing all of your data. It's also where your workers actually live. It's the CPUs and the memory that is actually going to process that data for you, evaluate those queries, and compute results. So when we're at Google, a lot of these concepts were actually exposed to us at a very low level, and we had to make decisions about how we stored the data and processed it in order to make sure that our pipelines worked fast. Typically in a kind of, you would see this if you've stored very large files on disk. You would store data in hundreds of blocks, maybe thousands of blocks. Each of those blocks is limited in size. So when we come to compute and actually read that data, we can spread those blocks across a number of different workers, with each worker processing a portion of the data. This is a somewhat simplified view in the example of reading or aggregating like a single table. but it generally applies to multi-step transformations or extremely complex queries. We can keep applying the same concept here. So if we have these blocks on the left, in this case just 4 simple blocks, we could run our single worker against all of those blocks and process them together. In another case, we could spread that work out across a number of different workers themselves, with each one having to read a single portion of the data and compute some aspect of some aggregation. This can then be re-aggregated in future steps. This is kind of the basic idea around things like MapReduce, which are core to systems like Spark. Cloud data warehouses are making this possible on all kinds of queries, and they're making it possible to dynamically scale up and down extremely quickly. So if you decide to read a petabyte data set in a product like BigQuery, it's going to go and spin up possibly thousands of individual workers for you, each of which can go and read a portion of that data to keep things running in parallel. OK, so these are a couple of innovations that make modern data warehouses scale extremely well. Ultimately, this is enabling the ELT model. If we couldn't afford to dump all of our data in the warehouse, then the ELT model wouldn't work. But thanks to the scalability of modern warehouses, this is now possible. OK. So to dig into the T a little bit more, every warehouse out there is possible to write SQL queries. It's possible to create new tables and build transformations based off purely by SQL. There are a number of operational challenges to doing this at a large scale. And we're going to kind of dig into some of those limitations now. Cool. So when we're working in an ELT space, there are a few things we want to achieve. For a start, we want to be able to version control our code. We should be able to reproduce our data stack if we somehow lost all of our derived transformed data sets. So by version controlling a code, it means we have a record of what exactly was the logic that produced those derived data sets so that we can rebuild them if we need to. Additionally, avoiding mutation of data sets, avoiding insert and delete operations, this helps us maintain reproducibility. It means there's no state that has to be managed in our data transformation pipelines. And it means that, again, if we lost everything, we could reproduce it from scratch. Another important thing to watch out for here is if our source data sets are not event-based and are actually mutable themselves, then it can be extremely hard to define a truly reproducible kind of data stack. So for example, if you maintain a copy of your production database in your cloud data warehouse, you could snapshot that every day, and that would be fine, and you could overwrite that snapshot, but you'd only ever have a view of the latest data. An event-based model would simply add a new row every time a row in the database changed to some table in our warehouse, which means we've got a complete history of how everything changed and enables us to rebuild our derived tables from scratch. So another objective for us when we're designing our ELT stack is we want to be adopting software engineering best practices. And I think this fits kind of into the general data ops theme. There are a lot of ideas that came from a DevOps world where we want to make sure that we're building reliable, tested software. A few of those things, there are many things here, but a few of those things that I think particularly apply to this kind of case is we should be writing tests. It's pretty standard to write tests for code. If you're building an application, then you should test it. And we often don't have that in a data setting. So being able to write tests in a SQL environment is extremely important. Having code reviews and style guides, these are somewhat optional, but are a great practice to follow and kind of build on top of this idea that all of our SQL code is version controlled. Using continuous integration and release processes We shouldn't be modifying production directly. We should have processes to roll out new versions of our data applications. So these are some of the things that we're trying to achieve. And we'll go now into how we can actually accomplish some of these things and what that tooling looks like. So as I've said, in an ELT model, SQL is our primary tool for transforming our data. And there are a number of reasons why we love it. So from my perspective, SQL is our best chance of building a common language for data across an entire organization. Something that works for both the software engineers, for the data analysts, and possibly even the business person. SQL is relatively simple to understand. It's still a step up, perhaps, from some of the things we're familiar with, but it's our best chance of getting there. We've mentioned how modern warehouses scale extremely well. It's very easy for us to iterate quickly on SQL scripts. We can write a query and generally run it against our warehouse almost immediately. We don't have to build and compile code or deploy it or wait for clusters to spin up. And this kind of makes the overall development process quite fluid and easy to debug, particularly when we can just run a query and see what the output looks like. SQL has a number of other benefits as well, and this ties again in some of the stuff we talked about, cloud warehouse scalability. Because of SQL's language, and the fact that it's a declarative language compared to other languages like Python or JavaScript or pretty much anything else, there's a lot of automatic optimization that can be done and a lot of things that can be done in parallel for us. There's another nice side effect of this, which is SQL queries generally don't have any side effects, which makes it a lot easier for us to reason about our code and the effect that it has on the data. SQL queries are also guaranteed to eventually terminate, usually, not always. So SQL also has some problems. It isn't a proper programming language, which means that actually building some of the things that we have initially set out to achieve, like having release processes and being able to write tests or promoting code reuse, are actually extremely hard to achieve with SQL in its pure form. The reason I held back on the previous slide is because actually there are some flavors of SQL, like T-SQL, if you're used to SQL Server, which actually allow us to do some of these things, where we can't necessarily guarantee the completion of a code, but the expressiveness of T-SQL is a lot more powerful than pure SQL. So ultimately, the thing behind all of these issues is that SQL is not a real programming language by most ways that you would define it. It has no control flow. We don't have if statements. We don't have for loops. There's no recursion or iteration. This makes it extremely hard for us to do things like develop multiple environments or manage release processes for a SQL-based data transformation layer. So we want to address some of SQL's pitfalls here. And to summarize those things, there are many reasons why we love SQL, but really what we want to accomplish is bringing release processes, version control, testing, and promoting code reuse in our code bases to SQL. And these are the things that we kind of set out to fix with Dataform. We'll kind of dig into Dataform now and how it addresses some of those. Okay, so Dataform is a couple of things. We'll cover the open source framework first. It's developed in TypeScript. It has support for BigQuery, Redshift, Postgres, Azure SQL Data Warehouse, Snowflake as well. It has a number of built-in abstractions and APIs that make it easy to accomplish some of the things that we're trying to do. The first concept, actually, let's skip ahead for a second. So the first concept that we want to kind of get across is when we think about data applications, we typically think about these data flow graphs or like directed acyclic graphs, where every operation in our data pipeline, it has some set of dependencies that need to execute before it or some input data. We can represent it with a diagram like this. In this case, each of these squares is some data sets that we want to create. These aren't supposed to just be pretty. They are genuinely a very good way for us to represent data applications. And that's how we want to think about our data pipelines with Dataform. We think about them like software, like an application, and we are aiming to give you the tools to manage them like an application so that we can follow the normal development cycle of building, testing, documenting, and releasing that software to our data warehouse. So the Dataform framework makes it easy for us to write parameterized SQL. It makes it easy for us to reuse code so that we don't end up copy-pasting the same SQL queries all over the place, and bring some consistency towards our data definitions across the company. It has APIs that make it easy for us to build these directed acyclic graphs that we just looked at. We can also write data assertions. These are tests. We can check that our data conforms to some certain format, or that it has a certain number of rows, or that there are non-nulls. It also has support for documenting data sets and developing, staging, production environments, and managing those release processes. So this is all in the kind of core open source framework, which we released in the last year. So in our graph, there are a few different action types that we think about. By far the most common one that we want to achieve is publishing a new data set. Generally, what we find is that most data sets we want to build can be built off some other data sets that have already been built by somebody else, rather than trying to rebuild that from scratch. Dataform makes it easy for us to share that and publish new data sets built on top of other data sets. We can also execute arbitrary SQL. Sometimes we have use cases for this. We might need to delete rows or do inserts. We can run our data assertions, which check for data quality issues. We can run unit tests, which are slightly different. And we can also declare external data sets, which may have been produced by other third-party systems that are outside of a Dataform project. So the components here are a few things. There is a data flow graph format, which allows us to represent this flow of data through our application. We have a new language for SQL called SQLX, which is kind of platform independent and allows us to kind of abstract away some of the common repetitive tasks that we do with SQL and make certain things like templating and tagging different data sets extremely easy to do. We also have a compilation process, and again, I mentioned some of the abstractions for common tasks like publishing a table. We don't have to think about writing create or replace table statements or dealing with temporary tables. That's abstracted away by the framework. We can just think about defining the data sets as a select statement, and they'll be produced and updated for us automatically. So this is by far my most technical slide. So I have two examples here. On the left is a SQL file, just a plain SQL file, where we create a table with a name as a select query. It's a pretty straightforward example. We're selecting from a table called users. We're doing some grouping and some aggregation. On the right, I have the kind of Dataform equivalent. So there are a few kind of key things to point out here. First is we omit the create table statement directly. Instead, use this config block to tell Dataform what kind of thing it should be produced in the data warehouse. Maybe it's a table, maybe it's a view. We have this same query again with some variables kind of built into the syntax so that we could actually control properties of our SQL queries from a single place, from a common set of variables or constants. And the final thing here is we have a special function called ref, which allows us to reference another data set. The purpose for this is to build up the dependency tree that we saw previously across our whole project. So we don't have to manually define all of those connections. When we pull data from another table, we can automatically infer a dependency, which means you can just worry about writing your SQL and referencing other table sets, and the dependency graph will be built automatically for you. So we take our SQLX, which is not pure SQL, and we run through this compilation process. I won't go into the details of this. It's taken from another talk. But ultimately, what we get out at the end is a set of vanilla pure SQL that we can run against our data warehouse with no Dataform-specific aspects to it. And that SQL and all of the references get resolved, and we end up with a data structure which represents a graph like this. And this is an example we took from our actual project, our internal data project. Cool. So I'm going to skip through these relatively quickly because I don't think they're too important. One of the things we said we can't do with SQL is write for loops. So we have a very common use case which a lot of our users have, which is they have a ton of data sets that they produce in their warehouse which contain PII. They want to delete all rows for a given user from all of those tables if they request to be deleted from, if they request to be forgotten through kind of GDPR processes. So we end up writing a ton of delete statements across a ton of tables, which can be kind of time-consuming and somewhat repetitive. So Dataform's APIs allow us to actually introduce some of this control logic and for loops, where we can generate SQL for a number of different tables and build that into our graph automatically so we don't have to copy-paste the same query a number of times. Here's another example where I've got the kind of Dataform code on the left and the pure SQL on the right. If anybody uses Redshift, there are some operations you often end up doing which can be quite complex. For example, loading data from S3. Often you're working with temp tables, renaming, altering things. These are kind of hairy bits of SQL which you don't want to write over and over again every time you want to do this. So Dataform makes it easy for you to package this stuff up into APIs that you can reuse. So you have a standard way to load some data from S3 into your data warehouse, and that's done consistently across the whole company. So kind of final few minutes then. This is great, but it's still pretty technically complex. And with a new language, if we don't have an IDE or great tooling around that language, then it can be pretty useless. So when we developed Dataform, this was really our primary objective. We wanted to focus on the developer experience of working with SQLX and working with Dataform projects to make sure that that was extremely pleasant. So Dataform's platform, Dataform Web, has a number of things. Primarily, it is a integrated development environment for Dataform projects. So it compiles your code and sends errors and warnings as you write that code. It validates your SQL against your warehouse in real time. And it has full integration with Git, so you have version control, and you can manage CI and CD processes, release processes, code reviews, however you want to do that. It also has a number of kind of built-in things that you would expect from a data transformation tool, such as pipeline orchestration. So we will do scheduling and notifications and run logs. And one thing that we touched on briefly, with the Dataform framework, you can document data sets. So you can describe the columns, the fields, the tables that you create. So if you're going through a data cataloging initiative, Dataform makes it very easy for you to push that information somewhere to the graph itself and present that back. So here's just a couple of quick slides on the Dataform web platform, which is kind of like an IDE. You can develop SQL, run queries, run parts of your pipeline. There's Git integration at the top. You can visualize the DAG and visualize changes that you make as you develop, and see, understand how your lineage works across your whole project. And then finally, you can view the catalog, where you may define information about datasets on the left, and we kind of present that in a way that can be presented to everybody across your company who's looking for data and trying to understand what datasets to look at. Cool. I'm done. So there's a couple of links here. First off, to our open source framework. There's a whole documentation site on how to get started with Dataform, either through our command line interfaces or through the web platform. And the web platform's free to try. If you want to sign up and start writing some SQL, connect to GitHub, you're very welcome to give it a shot. Thank you.